Okay, so we are going to develop a couple theorems which will make it easier to do some probability calculations. So to do these theorems, we need something to start with, and we're going to use these three properties of probability functions that we talked about a little bit earlier. So we remember, just to repeat it again, that the probability of any event has to be between 0 and 1. The probability of the whole sample space has to be 1. And the probability of a union of events, so here we have a bunch of events, the union of them. We can take union and turn it into the plus symbol. So we get the probability of E1 plus the probability of E2, and so on, as long as these E1 through EK are mutually exclusive events. So sometimes if you're faced with having to compute the probability of a big event, if you can break it up into the union of smaller events, it might be easier to calculate, and this allows you to do that as long as these events are mutually exclusive. Okay, so we have these three properties, and then based on these three we can prove a few additional properties or a few theorems. Also, we're reviewing here again that if we have a verbal expression like the probability that E does not occur, that's the probability of E prime. The probability that E and F occur, that's the probability of E intersect F. And the probability that E or F occurs, that's the probability of E union. So once again, union is or, intersection is and prime or complement is not. Okay, and again, looks like they're repeating that here again about mutually exclusive. Okay, so so if they're mutually exclusive, then the probability, so these are mutually exclusive, right, because they have nothing in common. In that case, we can use this rule. Okay, here's the first theorem. The probability of the empty set equals 0, where theta is the empty set. Now, we already made some kind of justification for this, but we're going to kind of lock it in now by proving it. Okay, for any event E, so how do we prove this? So how would you prove that? How would you prove that this is true? So it doesn't sound so easy at first, but actually it's very simple short proof. And let's look at it. If you take any event E, now you might say, why are we considering an event E? We're talking about the probability of the empty set. So it's, why are they starting this way? Maybe they tried many different ways, and finally they came up with this. Okay, so anyway, for any event E, they say, of course, E union the empty set is E. Okay, and also E intersect the empty set is the empty set, right? That's obvious. But this has a special meaning, right? What does this mean? If something, if the intersection of two sets is the empty set, then what do we call the two sets? We say they're disjoint or mutually exclusive. Okay, so these two events are mutually exclusive, but they're so therefore, if I wanted to write the probability of this union here, what can I do? Since these two are mutually exclusive, I can change union to plus, and that's what they did. So what they write is, we had E equals E union EF, so we can start out with the probability of E, but we can replace E by this, which is what they do here. But this, they can change this to plus because we said that these two are mutually exclusive, so we get that. So you have this statement: the probability of E equals the probability of E plus the probability of the empty set. Therefore, the probability of the empty set has to be 0. Okay, so that's now we've proved this, that the probability of the empty set has to be 0. So we wanted to prove that, and we did. Now they say, okay, maybe it's not just an abstract theorem, but might be useful. If a fair die is tossed, what is the probability that the number on the top face is even or a 5? And then secondly, what is the probability that the number on the top face is a 7? Well, we already know that 7 is impossible, so it's going to be 0, but let's just go through it. We assign the uniform probability model to this experiment. What does that mean? It means that what? All of the outcomes are equally likely. So all the faces on the die have the same probability. In other words, they all equal 1/6. The event G, that the number tossed is either even or a 5, is this event. The event H, that the number showing is a 7, is the empty H is the empty set. Okay, thus the probability of G is 4 over 6 or 2/3, and the probability of H is the probability of the empty set, which is 0. They said, note that we can obtain the probability of G in another way. We have that G equals E union F, where E is even number and F is getting a 5. So G is either getting an even number or getting a 5. So we can write G like this, E union F. But this E and this F are mutually exclusive, right? These don't have anything in common. This one and this one have nothing in common. So E union F is mutually is the empty set. So they're mutually exclusive. So we can say that we want the probability of G equals the probability of this, but the probability of that can be split up. Union can be changed to plus, so that we get the probability of E plus the probability of F. So we get 3/6 plus 1/6, which is still 2/3. And they remind us here that that doesn't apply if E and F are not mutually exclusive. In fact, they say the next theorem applies to any events, whether they're mutually exclusive or not. So whether they're mutually exclusive or not, we can say that the probability of E union F is equal to the probability of E plus the probability of F. It sounds like the mutually exclusive case, but we have an extra term here, minus the probability of their intersection. And why is that true? Let's look at the proof. They say, as shown in figure 2b. So here's figure 2b, and here's E union F, and they're saying we can write this as the union of this, this, and this. Now what is this, what is this, and what is this? So this one is E intersect F prime, right? Because here's F. F prime is everything outside of there, and the intersection of everything outside of there with E is exactly this region. And of course this region is E intersect F. And then what's this region? They say that this region is E prime intersect F. In other words, it's everything, here's everything outside of E, and the intersection of that with F is this region here, which is this region here. So we can say that this is the union of these three sets. And what else can we say about these three sets? What else can we say about these three sets? They're disjoint, right? So we're writing this as the union of three disjoint sets. These three disjoint sets. So let's look at that now again. So E union F equals where is it? Is equal to, here's the first disjoint set that we said, here's the second disjoint set that we said, and here's the third disjoint set that we said. And where the three events on the right side of the equal sign are mutually exclusive. So these are mutually exclusive. So therefore what? So we can change union to intersection. I'm sorry, union to plus. So we did that, plus and plus. So we get that the probability of E union F is equal to the probability of the first one plus the probability of the second one plus the probability of the third one. That's what they have here. Now, notice that this piece is the probability of E, right? Let me look at that picture again. The probability of E is this plus this, right? This is E. This is E. So this is E. So the probability of E is this piece plus that piece. So this piece plus that piece is the probability of E. And the probability of F, similarly, is this piece plus this piece. Now, the probability of E union F is this, is this three-part sum here, right? But if I said, oh, the probability of E union F is P of E plus P of F, what would I be doing wrong? So if I said it's P of E plus P of F, I'm saying it's this plus this. So what am I doing wrong there? The real answer is it's this plus this plus this. But if I said it was P of E plus P of F, I'd be saying it's this plus this with this one again included. So I would have included this one twice. But that's not right because it's only there once. So how do we fix it? We subtract this out once. So we said it's P of E plus P of F, but when we do that we're counting this one twice. So we subtract it out once, then it's okay. So that's what we get here. Okay, so now what's this? So let's look at this. So this is always true, whereas we had a different theorem that was only true when the events were mutually exclusive. What was that other theorem when they were only mutually exclusive? We had a theorem that just looks like this. So if they're mutually exclusive, this equals this. If on the other hand, in all cases, this equals this. So what happens in all cases if they're mutually exclusive? What happens to this term? Well, if they're mutually exclusive, then this is the intersection of the two of them, means this is the empty set. So we have the probability of the empty set, which we said is 0. So we do get just this statement if they're mutually exclusive. Okay? So obviously when they're mutually exclusive it's easier. We don't have to worry about this. On the other hand, if they're not mutually exclusive, we have to pay attention to this term. Okay, let's take a look at this. An example where we can use this theorem. A card is picked at random from an ordinary deck of 52 cards. Find the probability that the card is a club. Now remember that a standard deck of 52 cards has 4 suits, they say. There are clubs, spades, hearts, and diamonds. And there are 52 cards, so that means if they're divided evenly between clubs, spades, hearts, and diamonds, that means there are 13 clubs, 13 spades, 13 hearts, and 13 diamonds. Okay, so find the probability that the card is a club, the probability that the card is an ace, the probability that the card is either an ace or a club. So let's see how we can do these using this new theorem that we have. Since the card is picked at random, so when we see that it's picked at random, that means we're saying that all cards are equally likely to occur. That means we're saying that we have the uniform probability model. Thus the probability of each sample point is 1 over 52. So let C be the event that the card is a club. That is this that we're looking for. The card is a club. Since there are 13 clubs in the deck, the probability of C is, so there's n elements in C, and there's 52 elements in the sample space. So the probability of C is equal to n of C divided by n of the sample space, right? That's because we can use that because we are assuming uniform probability. Okay, so here's the answer. Now the probability that the card is an ace. Well, let A be the event. So it's always good to define an event for what you're seeking the probability of. So we're seeking the probability that it's an ace. So define such an event. Let A be the event that the card is an ace. Since there are 4 aces in the deck, there's only 4 aces. N of A is just 4. So we get n of A over n of S. N of S. So we get 4 over 52. So and this is because we can do that because it's the uniform probability model. So that's the probability of an ace. Okay, now the probability that the card is either, how do we interpret the word either? We use intersection, right? So either an ace or a club, or how do we interpret the word or, I should have said, I guess. So either an ace or a club means either a club or an ace with union in the middle. But now we can use this theorem. So what does it say? It says that this will be the probability of C plus the probability of A minus the probability of C intersect A. So what is C intersect A? That means what? That it's both an ace and a club. That means what? It's an ace of clubs. There's only one ace of clubs. So what's the probability of this? 1 over 52. And what's the probability of this? We already did this one. And what's the probability of this? We already did this one. So we're done. We just put them in. So we put this one, they said C of P of C intersect A is 1 over 52. So we just put them in. This plus this minus that equals 16 over 52 equals 4/13. Okay. Alright, let's stop here and then we'll come back and do another few theorems, I think, or at least one more, I think. And then we'll talk about odds as well.